I'll try to wrap this up. This is a lot of nanoscience and stuff. It's complicated, and I put in a lot of the science behind it. You guys, it would be hard to explain all this in 15 minutes, let alone 4, so I'll try to do my best. Alright, so the title is Ferro Magnets in the Shielding of Medical Technology. As the title suggests, it's basically using some magnet structure to shield something that's delicate for external pulses of electromagnetic impulses. So like if an EMP went off, let's say, and you had like some circuitry that was delicate, the EMP blast would break that circuitry up and kind of mess up the entire situation. So I'm focusing on a way to shield technology, medical technology, it's a biology class, like a pacemaker or something like that, so that if an EMP blast goes off, you're not dead on the floor in 5 minutes. So that's a pretty narrow scope for this thing, but it works for all technologies, it's not only pacemakers. You can put this in anything that you want. I know SpaceX is talking about going to Mars, and it costs like $200,000 to do that or something. They obviously want to shield their technologies because Mars is a planet far away, and they want to make sure the stuff doesn't get messed up over there. So that's basically the introduction and setting up the issue at hand and how I will solve it. So this is again talking about the relevance. I focus mostly on EMP attacks, but again, this goes much farther than just EMPs. You got solar flares in space and whatnot. This is just an outline, basically. And this quote I got here from one of the research papers kind of tells you what exactly an EMP would do. It would just crumble society. And if you have like a 2 megaton nuke go off, it'll kill everyone in the radius of the nuke. The EMP blast will spread 1,000 kilometers in the area and destroy all technology. Cars wouldn't start up, the batteries would be fried. A lot of databases would be wiped. People in hospitals would die because the technology in those hospitals would fail. If they have a machine that's helping them breathe, they're dead. If there's any sort of technology-assisted living device, whether you're diabetic or whatever, you're pretty much dependent on those things, and so we need to shield those devices. So the object of this, I've mentioned it many times, is just to protect this technology. So we'll get into my hypothesis. There's a lot of different methods of protecting from electromagnetic pulses. And the one that I've chosen, there's a lot. The one that I've chosen is a Faraday cage. And Faraday was a smart guy working at Tesla, and he basically just was working on electronics and how circuits work together. He discovered that if you put a cage around something that's grounded, and you put an external electromagnetic pulse into that thing, it'll absorb it if it's a ferromagnet. And only a couple things are ferromagnetic under just regular conditions, so that kind of narrows down the materials that could be used. Again, I've added a quote to kind of talk about what the Faraday cage is. Alright, so I'm thinking we need it small, so it fits around circuitry and whatnot. We would need a ferromagnetic nanoparticle structure that goes around a pacemaker or whatever the circuitry is, and it would basically protect you from the EMP. But there's a lot of things that go into this, a lot of things that you have to consider when you're thinking about materials to be used and how they react with the human body. So it needs to be water soluble if it's external, or something that your body wouldn't attack and would agree fine inside the body. So this is basically the method. It's pretty broad, and I'll go into detail on each of these topics in a second. But it starts with the concept. There's a lot of different factors that go into this, and you can't just say this is the best answer from the theory. You have to do a lot of testing, and you have to derive more theories even to see if this would actually be relevant and if it would be plausible. So that's the first step. Then once you have your material that you want to use, then you would make it, obviously, and then you would start structuring it around the device, whichever you would use. And this is another set of issues with the structure because there's a whole bunch more parameters inside of magnetic materials. They move around magnetic fields and things like that, so the distance away from the circuitry would be considered. A lot of factors like temperature would be considered, and things like that. And so this is a very difficult process too. It takes quite a while to do testing and things like that. So then after, like I said, testing, after you test it, it works, doesn't work, whatever, you revise it, make sure it works better, and then you get your output. So that would be the entire course. Again, this is really broad. So let's get into some of the details of first thing I mentioned, which is the synthesis and what material you use. Okay, so like I said, we're considering a lot of different things for these particles, especially a ferromagnetic particle, and now we're going to go into some nanoscience. So basically, there are a couple different elements that are ferromagnets: iron, cobalt, nickel. Those are the relevant ones. These ones you wouldn't really consider because they're below the J, X integral, and that would mean that you need to get these materials, but they also need to be stable inside the human body, so that's another consideration. And so, yeah, probably iron would be your best bet. And then talking about the different types of ferromagnets, you have the medium which it's in. Changes a lot of things. So if it's inside the human body, it has a different medium, and that changes a lot of the ferromagnetic properties. So this is a consideration as well. And talking about magnets in general, the difference is you need a ferromagnet because the regions are already aligned without an external field. With a paramagnet, they are not aligned, which means that they're not as powerful until the field happens. So basically, a paramagnet is something that is not magnetic until it is exposed to a magnetic field. So we need this one because it needs to be magnetic on its own without the magnetic field touching it. So that's basically what that's describing. And then another consideration is the size of the particles that you use, because as you reduce the size, a lot of there's regions inside of the magnet, so it's cut up into various regions. And if the regions are all pointing in one direction, which is what they need to be doing, it will be ferromagnetic. If they're not, then it will be paramagnetic, but you need it to be a ferromagnet, so the size that it's at changes that. And as you get to very small sizes, there's only one region. And that's very bad because it becomes a super paramagnet. When it's a super paramagnet, the coercivity is 0, which basically means the direction of the magnet is all directions at once. So it's not good. You have to really consider the size, those type of things, and that's another boundary that we talked about. So again, this is showing all the different regions of the size compared to a magnet. And as it's large, when you get smaller, the regions decrease until there's 0. And then basically you'll have the arrow could be pointing anywhere because there's no region pushing it into one direction. So this is talking about the temperature effect, which is a big part because when it's a super paramagnet or a paramagnet, the temperature affects whether it is spinning around in random directions or it's staying in one direction. If the thermal energy is above the magnet's coercivity, then it will be spinning around. The thermal energy will effectively be enough to counter the magnet itself. And so if it's in the human body, you're going to need to consider this. This equation implements a lot of the size dependencies and what material you're using. This is just a graph showing the difference between a ferromagnet and a paramagnet. And the main difference is right here. It's magnetic right there without a field applied to it. This one is not. It's at 0, 0. That's the main difference. Again, we'll talk about that. And then the blocking temperature is what I was just talking about. If it's over that, you have a super paramagnet, and then that's not what you want. It's not ideal. So basically you need to consider all of those things as well as the different ways that your body could react to this thing inside of it. So it's a lot of consideration for each of the things. And just getting into the foundation more broadly, I feel like technology is a really important thing for society as a whole, and it relates to biology in a lot of ways. And I think that this project itself is very important because if you think about what technology has functioned as in society, it has effectively slowed down the process of natural selection, which has prevented human species from evolving as much as the biosphere has. And that means that over a long period of time, as the biosphere molds around us, we're not evolving with it, and we'll need the technology to stay, alive. Things could become very toxic. Things could the synergy between animals and plants and things could change in our millions of years of living. Obviously, it doesn't happen in one day, but keeping the technology able to do stuff like this to keep you alive. What if we have to move to a different planet that is extremely there's a pulsar next by and there's gamma ray bursts and EMP bursts every single day. It's just kind of talking more broadly that we need to invest a lot in technology because we owe our lives to technology. So that's the whole idea. And then these are my references.
Okay, like try to solve this problem to maybe?
I think it would probably be easiest to answer that by saying companies who would not want this. This is a way of protecting any circuitry device. This is a way of
Testing 1, 2, test.
It's a way of protecting circuitries, which is in like all technology. This is something that could save lives. You could put it in spaceships to have more reliable instrumentation. You think about different microscopes and things like that that use transmission electron, that you could have more stable calculations if you were able to limit the amount of magnetic fields applied to those various things that you're observing. So,
Paul, you have a question?
What do you think the effects would be on the human body with the magnet? Because our heart beats off of electric impulses, and then there's the iron as well.
okay, so it's important to understand the difference between magnetism and magnetic fields. They're not the same thing. And basically, with the magnetic field that's applied to a superferromagnet, its effects are minimal. It's not like the magnets are pulling it out of your blood or anything like that. They're not strong enough to do that, and the field applied is not great enough for it to have any real effect. But one thing that I've already started trying to, which is what I've done, I've just been trying to predict different things and different problems that you could run into, things that need to be considered. One of the main things, so it's not off your topic, but one of the main things that needs to be considered for this is basically when the body absorbs that magnetic field, that energy doesn't disappear. It's transferred into heat energy, and so it could basically burn your chest because the magnets would heat up, and that could be a bad thing. And then talking again about the blocking temperature, if the temperatures get too high in the magnet, it changes its magnetism, and that's not good because it's not reliable. So I guess a couple ways of countering that would be putting some semiconductors around it, and then an insulator of some sort. And these are all considerations. Like if you're making a structure built out of nanoparticles, it's not very strong. It won't hold itself together. You need other things around it to hold it in place. So there's still a lot of work that needs to go into it.
Okay, so you did have a lot of thoughts in that, but I don't see what exactly you're trying to do at the end of the semester. I mean, what exactly is the main point after this? Because it's a whole concept. You're presenting a very broad concept, so are you trying to target one specific device, or
No,
what is your?
I
What
basically
is
want
your
to see whether or not this is something that can be done.
So are you
That's
trying to
the
come up with a model that magnetism, as this magnetism is applied, and so at the end of the semester I can see a mathematical model of predictability? Is that what we're driving at? You've got so much idea. I just don't know where are you going to be leading to at the end of the semester. You have to narrow it down where there's one target. You can go as far as paramagnet or magnetic field or magnetism. Which of these exactly are you going to be focusing on at the very end? That is, I think, the biggest problem. Yes.
So basically, all projects have a lot of factors, and the more research you do, the more you realize that it's doable or it's not doable.
Mm-hmm.
If you do a lot of research, you see that it is doable. That research needs to be done first before you just jump into doing the concept. So basically, the object of this would be to check all the theories, see if it would fit into what I'm trying to do. If it would, then I could go farther than that. But I don't have the resources to start making this technology or anything like that.
No, you're not. I'm not expecting that.
Right.
I'm
I just want to
expecting
see if it's plausible or not.
No, I'm expecting because all of the theories that you have, in terms of the concept of magnetism and all of that, it's there. You already presented all of that. That's already in the bag. What I wanted to see is which exactly of these are you going to conceptualize on your own and put into an actual thought process. That's, I think, where you have to now start looking into, because you've got so much ideas.
What I'm saying is that's a question that can't be, that's something that I can't figure out what material to use, because there's different materials that could be used that have different effects. There's too many variables, and there needs to be testing done. I can't do the testing. So
No, you can't. You don't have to
I'm
be
just making
testing.
a model.
Again, this is conceptual. So if you want to model, for example, I want to see by modeling and applying the concept of paramagnetism, for example, I'll put it on a pacemaker. So considering all of that now, you have to put your temperature blocker in there, right? You have to make sure that the shield is not going to overload. For example, Those are the narrow parts, I think, Shane, that you have to put into consideration. Because otherwise, you'll be going into a literature review, which what I what I always tell students, do not just go into a literature review at the end of the semester. You have to have something that, kind of narrow at the very end. Because, I mean, it's very interesting, but you might get hanged into the literature review rather than, focusing on a very narrow.
Well, I'm just trying to be careful not to jump out on an iceberg and it breaks off, It's.
No, you're
I
not,
can't-
because that's why this is a conceptual.
Right.
Because you can always go and say, basing from the conceptual model that I have, this is not actually gonna work, and that's fine. Does that make sense? It doesn't have to be in a model where it has to work, but you can then say, if you actually use this material, it's not gonna work, because this is the output basing from my prediction according to my model. So that's, I think, where you would be, there will be a more tangible thing that comes out, because like I said, this is very, very broad, so you might want to narrow it down. And we are getting we'll talk to Shane more. Again, he's very famous because of these